Okay, class, let's continue on our discussion on some of the parameters used for your static lateral force procedure on the basis of the NSCP 2015 code provisions. So for the seismic zone coefficient, say, which actually is the zone factor that we are considering, and this actually is based on the site wherein your uh, your uh, earthquake acceleration, the peak ground acceleration, is actually based. So, in general, the Philippine archipelago is divided into two seismic zones only, and those are the Zone 2 and the Zone 4. Unlike other regions wherein they have four divisions, so we only consider two. And the most part of the region, are the Philippine archipelago, is actually located in Zone 4 region or Zone 4 factor. Okay, and these are those which are not a part of the provinces of Palawan, Sulu, and Tawi-Tawi. Okay, except of course the part of Busuanga wherein you can consider it as Zone 4. So all those which are not a part of Palawan, Sulu, and Tawi-Tawi, we immediately or automatically assume it to be located at Seismic Zone 4. So Tarlac is actually a Seismic Zone 4, while the others, which are Palawan, Tawi-Tawi, and Sulu, are in Seismic Zone 2. So you can see basically the map in which there's a subdividing line between the Zone 2 and the Zone 4 here, okay? So the structure period T is computed on the basis of two standard formulas in the NSCP. Although T can be computed using other tools, we can just, for simplicity, use method A and method B of the NSCP for static lateral force procedure. And method A is simply defined in terms of function of your height, wherein basically T is equal to CTHN to the 3/4. The old formula that was used here is actually much simpler, wherein your period is actually 0.1 of your number of story. Okay, so in other codes, old codes, you can see this formula. So if you know the number of story, let's say it's a 10-story building, then your period, okay, is simply 10% or 0.1 of 10, which is 1. Okay, so for a 10-story building, if you are using this, okay, for a 10-story building, your T now becomes 1 because N means the number of story. Okay, it's much simpler. But of course, the number of stories depended on the height. That's why here we change the N into a height there, the total height of the building, HN. Okay, but what really is a period? Okay, what is T? Okay, T is the reciprocal of frequency, 1 over F, where F is in cycles per second. Okay, so F is in hertz. Just like how you measure the frequency of a, a radio station, okay, in hertz, kilohertz, megahertz. Okay, so you have F as your frequency of vibration. So if in terms of radians per second, your F is simply equal to 2 pi over mega. Okay, so that is simply in terms of radians per second. Okay, RPS. Okay, let's check it if that is, yes, R per second. Okay, so what is really the period now? The period, which is defined as the reciprocal of your frequency, is now your natural tendency to react when there's an earthquake. If the person is the one involved in terms of the earthquake behavior, then the person's reaction in terms of its heartbeat, okay, will actually definitely define your frequency or your period. No, so if in case an earthquake happens and your heartbeat becomes fast, then you can now set your period of vibration in terms of the how fast your heart is pounding, no, when there is an earthquake. It's just like a natural reaction inherent to the person. Here, what we are considering is the structure, of course, and not the an individual. Okay, so for the a formula of T is equal to Ct Hn to the 3/4. The Ct is actually a coefficient depending upon the frame used. No, so for steel frames, we use Ct equals 0.853. For RC, we have 0.731, and for all other types of buildings, we have the 0.488. Okay? So when the period is high, the frequency is low, and when the period is low, the frequency is high, because here we can see that there is a reciprocity relationship between the period and the frequency. So method B, using method B now, using this principle requires a little bit of more involved computation in the form of your delta. Okay, so you need to solve for delta, and of course you need to have the forces, no, in which your delta is induced. Okay, Wi is the portion of the weight located at the assigned level. Delta I is the horizontal displacement at level I. Fi is the lateral force at level I, and g is of course the acceleration due to gravity, which is 9.815 meter per second square. Okay, so note that the value of t in method B did not exceed 30% that in method A to make it as a self-checking. No, so your t B should be less than or equal to 1.3 TA. So this is the limitation for it. Okay, so we don't want to make an overestimate of your period such that your frequency becomes very high, or sorry, very low. Okay, so because they are reciprocal. So for the structural system, take note that this is only good for zone 4. This requirement is only good for zone 4, and for zone 3, TB is less than or equal to 1.4 TA. So this is zone 4, and this is zone 2. Okay, structural system coefficient R and the dead load weight W is actually your R, which I have introduced you in terms of tables. So R actually serves as the same function as RW and K in older versions. And W is the total dead plus 25% of the floor live load in storage and warehouse occupancy. So for the weight W, this is actually the pure dead load. And an additional 25% of the live load can be added to W in case the floor actually holds storage occupancy or a warehouse occupancy. Okay, for the vertical distribution of lateral forces, the formula is simply a function of your base shear, wherein the base shear, after computing it, can now be used to back compute your forces. Okay, so it's the other way around. So in the lateral force distribution or lateral force procedure, what we get is the base shear first, then we solve for F. Okay, so this is the first step. This is now the second step. Base shear first, okay, before we solve for F. And the base shear is given by formula above. And the Ft and Fi's, okay, so these are now the unknown, okay, and Ft is another additional force at the tip or at the top, okay, so it's actually a part of the base shear, which is called the whipping force, okay, the whipping force, okay, or the slashing force, okay. So if you have experienced somebody hit you by a stick, a very flexible stick, and then the tip of the stick hit you, there's actually an additional force that will be induced in at the tip to add up the total force induced on the whole stick. Okay, so it's a whipping force given by the formula 0.7 EV less than or equal to 25% of the base shear. Again, there's a limit here. No? There are a lot of limiting values. Please take note of that. Now, when Ft is, when the time, or sorry, the period rather, is less than 0.7 seconds or equal to 0.7 seconds, then your whipping force Ft becomes 0 such that your formula here will no longer involve an Ft. But if it is greater than 0.7 seconds, this will be considered, and therefore your Fi will be simply B minus Ft times a distribution factor. You call this the distribution factor based on the lateral force, static lateral force procedure. Okay, so this is Wx, Hx, summation of Wi, Hi. So these are now the definitions of the nomenclature. You just look into the definitions, and we can understand this better when we solve some examples on this. Okay, so let us now extend our discussion on how these forces are distributed again on the basis of story shear and story moment. Okay, so we need to find uh, a way on how to compute for the story shear and the story moment so as to check overturning behavior later. Okay, so Vx is simply Ft. Okay, there's an Ft here that is included on the base shear if your T is greater than 0.7 second. Okay, so aside from F4, there's an Ft here. Okay, so if I cut now, let's say this part here on the second story, X. Okay, X is the story in question. What will be my formula? So Vx will simply become equal to Ft plus or minus the summation of I equals I equals X. So what's my X? I start with 2 going to 4. Okay, I have a 4 story. Those is story 2 to 4. Okay, 2 to 4 of Fi. Okay, so take note on how to use the subscript and the range variables. While Mx now becomes simply the additional F top multiplied by Hn. What is my Hn? H4 minus H2 plus summation of I equals, sorry, this must be also X because we are referring to X. Okay, so this is now I equals 2 to 4 of Fi times Hi minus H2. Okay, you just substitute that. Okay, so we will try to use this formula later on our problems. No? So I just want you to know how to interpret this formula quite accurately. Now, for the horizontal distribution of shears and horizontal torsional moments, so these are the things you need to bear in mind. Okay, Vx is, in a story is distributed to the various elements in proportion to their stiffness, which uh, is done by providing 5% accidental eccentricity if there is no eccentricity. Okay, and the torsional moments occur if the center of the mass, of course, is not coincident with the center of rigidity. Okay, so mtx is therefore equivalent to vx plus or multiplied by E plus a certain eccentricity, which is the accidental eccentricity. In case E is equal to 0, then your torsional moment will be purely due to accidental eccentricity. So this just helps us understand that if we have here a certain, okay, a body, okay, wherein the rigidity of the body, say I have here the rigidity, uh, uh, the point of rigidity or the center of rigidity CR, and I have here the center of the mass CM. Okay, if I have an axis which is uh, directional on the basis of the distance between these two centroids, okay, we have two centroids in question. So this eccentricity will now create some torsional behavior on the body itself. Okay, when there's a shaking here, example, if this body moves back and forth like this, of course the center of mass will induce a force which is equivalent to the mass times the acceleration. Okay, so the force induced here now is actually the base shear that we are talking about in this particular example. Okay, so if this is now your base shear, which is focused on this mass, let's say V, then the torsional moment, it will tend to rotate not on the center of mass but on the center of rigidity. Okay, so this will rotate and create a couple that will rotate, okay, in a clockwise manner, which is called the torsional moment. No? So this is now your, of course, your acceleration, which is going back and forth. So in this regard now, this effect of torsion will serve as basis on the distribution of your forces unevenly. It's not equal distribution on points where the stiffness is placed. Let's say my stiffness is distributed somewhere. Here I have a column, there I have a column, here I have another column. So the forces induced here will no longer be equi uh, equivalent to each other. No? It will be based on the distance from which the center of rigidity is measured away from the center of the individual column uh, in question. Okay, so this is now the reason why we have to have a way on how to distribute it horizontally or laterally based on the torsional moments. Okay, so take note of again some provision on 2085.1.5 where in the overturning uh, moments in every structure shall be designed to resist overturning effects caused by the earthquake forces specified in the section 208523. Overturning effects on every element shall be carried down to the foundation. So this overturning computation actually is a provision in the code to guard against possible collapse due to overturning. There may be no collapse due to failure, but there may be collapse due to overturning. Just like any other structure, stability is also a factor of safety. Okay, so we just don't make use of analysis and design on the basis of a safety requirement on the material exceedance, material stress exceedance, but also stability on the part or the member concerned. Okay, so we have now here a sample of what I have described here in general of a structure which has an accidental eccentricity uh, which is 0.05 of the horizontal dimension h plus a certain eccentricity due to the offset of the center of mass to the center of rigidity. Okay, so here you can see a very symmetrical structure, but the center of mass may be off-centered because of some reasons, and the center of rigidity is also off-centered because of some reasons on the dimensions of the lateral stiffness. Okay, so this now will tend to create a moment, okay, couple, which is in terms of the base shear multiplied by the total eccentricity given E plus 0.05 H. Okay, so that is actually the same as what I have explained to you here on this particular uh, free body diagram. Okay, so we are through with the discussion here. So let's have an example problem to understand better what the formulas are all about on the next video. Thank you.